There are two more simple results of this I want to point out, and then we'll look at some more implications. But for simple results, we can rewrite this, and sometimes it's convenient to find out the average kinetic energy, average translational kinetic energy of molecules, and it turns out that is simply 3/2 K Boltzmann times T. And even though I worked this out on the assumption that all the molecules were the same, it turns out this holds even if you've got a mixture of several different kinds of molecules. So for example, in air, which is 80% nitrogen and 20% oxygen, this works out both for the average kinetic energy of the nitrogen and the average translational kinetic energy of the oxygen. Now we can also take this and remember that the average translational kinetic energy is just 1/2 m times the average of the velocity squared. I can solve this for that average velocity squared, and I find that the average velocity squared is simply equal to 3 K Boltzmann T divided by the mass of an individual molecule. This is the average of the square, so it's the mean of the squares. If I take the square root of both sides, I get what is known as the root mean square. It is the velocity that is the square root of the average, the mean, of the squares of velocity. So the RMS speed is simply the square root of 3 K Boltzmann T over the molar mass. Now you'll notice the only real problem with this, K Boltzmann is a tremendously small number, and I said molar mass, but this is the molecular mass. Molecular masses aren't easy to deal with. So what we would like to do is multiply both the top and bottom of this by Avogadro's number. Avogadro's number times K Boltzmann is just the ideal gas constant. And the molecular mass times Avogadro's number is just the molar mass. So the RMS speed is just the square root of 3 RT divided by the molar mass, or the mass of 1 mole of my molecules. And I can use this to find the RMS speeds of, say, hydrogen or oxygen here in the atmosphere. Let's do that as a quick little exercise just to understand about how fast atoms are moving, molecules are moving in the atmosphere. So let's look. V RMS is equal to the square root of 3 RT over the molar mass. Hydrogen, diatomic hydrogen, has a molar mass of 2 grams per mole. And nitrogen has a molar mass of 28 grams per mole. So if I plug that in here, the square root of 3 times 8.31 joules, or kilograms meters squared per second squared, per mole, Kelvin, times room temperature, well, let's say about 22 degrees Celsius, or 295 kelvins. And we divide that by a molar mass of 0.002 kilograms per mole. Moles cancel, kelvins cancel, kilograms cancel. I'm going to get meters per second left. Bringing up a calculator, I have 3 times 8.31 times 295 divided by 0.002. Take a square root. Excuse me, missed the inverse. Hydrogen moves at 1,918 meters per second. I'm just going to write that as 1920. Notice that's greater than escape speed from the Earth. By contrast, if I replace that with nitrogen, 3 times 8.31 times 295 divided by 0.028, I get a value that is much slower, although still very fast. 3 times 8.31 times 295 divided by 0.028, take a square root, 512, or 513. Still very fast, faster than the speed of sound in fact, but not quite as fast as hydrogen.